Alright guys, so remember from the previous video, in the previous video I gave you three definitions of an extreme value, and the first one was this one, right, where the extreme value was taken as the largest data point, right? So in this picture, this is the only extreme value. In this video I'm going to talk about how to find the distribution of this extreme value. So the title of this video is as follows: is distribution of distribution of extreme value under definition 1. Alright, so alright, suppose you have a data set x1 to xn which are independently and identically distributed with CDFF. So these are the data points that we talked about in the picture that I showed you earlier. So this could be the data values in the 365 days in the year, right? So these are the data values, the data. And the CDF, I'm sure you know what CDF is. CDF is the cumulative. If you don't know what it is, I'll write it down. It's the cumulative distribution function. Okay, CDF, right? Now, by definition 1, which I just showed you, by definition 1, the extreme value is the largest data. So this is the data that you have. According to the definition 1, we pick the largest data point, which is the maximum of x1 to xn. And I'm going to use the notation capital M, little n to denote this. So this is the notation I shall use to denote an extreme value under definition 1. Right. Now I want to find the distribution of this guy here. So what we need to do is to find the CDF the CDF of M and S is this, right? Remember, this is the definition. This is the definition of a CDF, right? And this is the probability that the maximum okay, and if the maximum is less than or equal to x, then each of the terms within the max has to be less than or equal to x. So this implies that this is equal to the probability that x1 is less than or equal to x up to xn is less than or equal to x, right? Now I'm going to use, in the next step, I'm going to use the fact that x1 to xn are independent random variables. So using independence of x1 to xn, we can write the joint probability as the product of these probabilities. Okay. Now we are told that x1 to xn each has CDF equal to f. This is the CDF of x1 to xn, right? So which means that this guy here must be equal to f at x, and this guy here must also be equal to f at x. All right, and hence what you have is this, right? So you have f of x raised to the power n. So this is the distribution of the extreme value under definition 1, right? Now the next question is, how does this behave? How does this distribution behave as n? Remember, n is the number of days. I mean, in the picture I showed you, n is the number of days, which is 365. But sometimes you are interested in not just 1 year, but you want to know what happens over 2 years, or 5 years, or 10 years, or 50 years, or 100 years. So you want to know what happens to the distribution as n gets bigger and bigger and bigger. All right, so that's the next thing I'm going to talk about. So let me take this away. So as I said a minute ago, people So we want to know the distribution of Mn as n gets bigger and bigger and bigger and approaching infinity. So that's the question that I'm going to answer now, right? So I want to look at the limit I'm sure you know that you must have done this in your first year. So I want to look at the limit of the probability that Mn is less than or equal to x as n approaches infinity. So this is the limit as n approaches infinity of and I'm sure all of you guys are experts in calculus, so you know what the limit of this is. It can take two values, 0 or 1. 0 if f of x is between 0 and 1, excluding 1, and 1 if f of x is equal to 1. Okay, because if you have a number, if this guy here is a number between 0 and 1, excluding 1, and you are taking a power to infinity, then it must be 0. Whereas if this guy is exactly equal to 1, then 1 to the power anything is 1. So that's why you have this limit. So the limit distribution is either 0 or 1, which is not something that is very useful. So this is not a result. Right, this is not a very useful result for practical applications, because you have a limiting distribution that takes only two possible values, 0 or 1. So the practical application, it can have a 0. Okay. So the question is, how can you find a limiting distribution that is practically useful, right? And to answer that question, I'm going to deviate from extreme value slightly. Just for the next slide, I will deviate from talking about extreme value, and then I will get back to extreme value, right? All right. Suppose, so this is a deviation from talking about an extreme value. Suppose you have a random sample. With expectation of xi equal to mu, so the population mean is mu, and the variance of xi equal to sigma squared, so the population variance is sigma squared. Now let x bar so I'm sure all of you know this is the sample mean. So let x bar denote the sample mean, right? there are two results about X bar, the sample mean, that you should know by now from given what you have learned in your first and second years. So the first result is the following, that is, we should take the limit as n goes to infinity of X bar. What you have is the population mean, which is mu. And this result, I'm sure you should have learned this, is known as the strong law of large numbers. Right? And so it says basically that the limiting distribution or the limiting random variable of X bar is mu, which is a fixed constant. So hence what you have here is not something very useful. So this is not a very useful result, not a very useful result. Okay, this is not a very useful result because of the fact that the limit is a fixed constant. Just like we saw in the previous slide, that when you take the limit of the distribution of Mn, what you get is a distribution that takes either 0 or 1. Which is not useful, right? All right, now let's look at the second result on X bar. Let's look at this. This is once again a result that you should know. You should look at the limit of this as n goes to infinity. Then this, I'm sure all of you know, this is the standard normal random variable, and this result is known as the central limit theorem. Right, or CLT, right? And CLT, okay? And CLT, as you know, CLT is a very, very useful result. There's not a single area in statistics where CLT is not used. Right? CLT is a very useful result. It's a very useful result. So what we have done is going from a result that is not very useful, we have gone to a result that is very useful. And what have we done? I mean, to go from this to this, instead of looking at the limit of X bar, we have looked at the limit of a scaled version. So we have subtracted a constant mu and divided by a constant sigma by root of m. So this here is a scaled version of this one. So let me write that. So from here to here, what we have done is we have applied a scaling. We have applied a scaling, right? By applying a suitable scaling, we have made sure that the limit, which is a constant here, is no longer constant. It's a random variable which takes the standard normal distribution. And that's what I'm going to do. That's what I'm going to do with the distribution of extreme value. Instead of looking at the distribution, the limit of the distribution as n goes to infinity, I'm going to look at the limit of the distribution of the extreme value after it has been scaled. So that's the next thing of this. The next slide of this video will look at the limit of the distribution of Mn after it has been scaled. Distribution of Mn, the extreme value, after it has been scaled. So to put it in words, we look at the limit of the probability of, instead of looking at the limiting distribution of Mn, we looked at a scale version of Mn. So I'm going to subtract a constant which I call Bn and divide by a constant which I call An. Right? So I'm gonna see how this probability behaves as n, the number of data points, approaches infinity. So we're gonna look at the limit as n goes to infinity of the probability that so this is going to be the same as the limit as n goes to infinity of the probability that Mn is less than or equal to Bn plus An x. Okay, and this is the limit as n goes to infinity of the probability that the maximum is less than or equal to Bn plus An x. Okay. Now, if the maximum is less than or equal to this, then each element within the maximum has to be less than or equal to the same thing. So x1 has to be less than or equal to Bn plus An x until xn has to be less than or equal to Bn plus An x. Okay. Now in the next step I'm going to use the fact that x1 to xn are independent random variables. So using independence, we can write this as okay. And in the next step, I'm going to use the fact that x1 to xn, each of them has CDF f. All right, so this will be equal to the limit as n goes to infinity of f at Bn plus An x, and similarly this is equal to the same f at Bn plus An x. Now each of these quantities is the same, so what you have is the limit as n goes to infinity of f Bn plus An x, that raised to power n. Right, now let me call this equation star. Now the question is, what is the limit what is the limit of star? In other words, if n goes to infinity, what do you get? What is the limit of this? So the answer to this question will be in the next video, and the next video will be about the extremal types theorem. The extremal types theorem is one of the most fundamental results in extreme value theory. It's just like the central limit theorem is fundamental for sample means. The extremal types theorem is fundamental for extreme values, right? Okay.